Hi, my name is Felix, and this is my 2CM4 design project. Also bear with me because I plan to, or this is basically going to be one shot, because I ran out of time, but that's cool. So first of all, what I'm trying to do is I'm trying to make an electric heater, or I'm trying to optimize it so that it can heat things the fastest by being able to have the most power sent into it at a constant voltage. So here are the background physics. I'm also changing the length, by the way. So I'm trying to change the length to optimize for the power. So here are the background physics. So first of all, I guess this is mainly description of the circuits, because I plan to put a lot more into it, like how the heat equation and heat works, but this is what I have, which is cool. So first of all are the Kirchhoff circuit rules. So first is the Kirchhoff's voltage law, which describes how the voltage drop in a circuit is equal to 0. So for this, what it just means is that all of the voltage that I provide to my simulation goes to my resistor. So that just makes it easier for me. Next is the Kirchhoff's current law, which explains that all of the current going into a simulation or going into a junction is the same as the current going out of the junction. So since I have no junctions for my simulation, it just means that the current is the same everywhere. So I can take the current anywhere from the simulation and it should be the same. Next I talk about Gauss's law, which kind of just talks about how in an enclosed space the electric flux is proportional to the amount of charge inside of the enclosed space. And in this course we kind of learned it in a more complicated way. Next is Ohm's law, which is really important, and that's just V equals IR. So after I used FlexPDE to model everything, and FlexPDE was pretty cool. But anyways, so first I added some equations to it, like E equals negative the gradient of the voltage. That's pretty important. And then I also defined the properties of the resistor, like the conductivity, the length, and the dimensions. And in the actual Python script, the length will be a %s because it needs to be edited in Python. Anyways, so after that, I guess I put some more equations into the FlexPDE script, and I also drew the shape of the resistor. And keep in mind that everything's in Cartesian too. I think I plan to make it, or it would have been better if it was in Cartesian 3, I think. But there's already the templates for this, so it was a lot easier. Okay, next I reported the length, the current, the resistance, and the power. And I tried to make it so that it would write to, or it would output to a text file, but it wouldn't work for some reason. So yeah. So after this is the Python scripting of the model. So basically, here I already mentioned it, but I had to change the length to %s so I could change the length of the resistor inside of Python. Next, I did a bunch of stuff. Here I'm making a list of all the lengths that I wanted to use, which is basically from 5 centimeters to 100 centimeters or 1 meter. And yeah. And this is the code to open the FlexPDE file and everything. And unfortunately, it didn't really work because, this part works, but the writing to the text file from the FlexPDE file doesn't work. So this is kind of how far I got with the Python. Then, as a result, as you can see, I couldn't really run the FlexPDE script, so I had to do this manually, and basically it looks like an exponential relationship, pretty much, where as the length decreases of the resistor, the amount of power that is dissipated by the resistor goes up exponentially. This is kind of weird though. And yeah.